Hello, my dear friends. I hope everyone is fine. So, in previous part, we left off here. We left off here where we calculated all the we ran the Dijkstra algorithm and we calculated all the shortest paths from source node to all the nodes. So our source node was A. So in case of A, from perspective of A, we have calculated all the shortest path. So two things needed addressing. So first one was how do we select the next neighbor? So we have to select the next shortest distance neighbor. Let me explain that. For example, if we are at A and then we are done updating the paths of A to its neighbor. So we have updated the path B of B and C, the distance of B and C. Now we would choose the neighbor with the shortest distance. So we would choose B. This is very important, and this ensures that we are traversing the shortest path towards our destination. And the other thing is, we can also include a parent attribute here. And whenever we update a path, for example, we have updated this path of distance of B, we can assign its parent. So from where this distance came from or from which node we travel and we get this distance. So for B, we have the parent as A, and similarly for C, we have parent as A. Then for D, we have parent as B, so and so on. So we use this updation of parents. It helps us when we want to determine the route because in traditional Dijkstra, it doesn't give us the actual route. It only gives us the shortest distance, which would be recorded on the node. For example, if we look at F, we would see that okay, F has the distance of 19 units from A, but we won't know which route to take from A to reach F. So in order to trace that route, we can use this parent attribute and we would just traverse the parents of respective nodes until we get to the source. So from F, we can see that its parents is E, and then recursively we can see its parents is D, and D's parent is B, and B's parent is A. So we can trace back the path towards the source. So now we would go to Visual Studio and start coding this. So before we start, let me make some things clear. We in this part we would see what kind of data structures are needed to create a graph and how we can create a graph in C and C++. We would look into that because it's very important that we understand how graphs are constructed and how graphs work in C and C++. Then we would be able to implement Dijkstra. So we would do that, and also we would get all the data to construct a graph from a file. So let me show that file. So this is our file. We would read the values from this file, and we can see that each line has a pattern. First one is source node, then the destination node. These are inverted commas. Then there is a label, which is the edge length or root length, and then there is a root label, and then the root length. So, for example, if this is a route, we have a route from A to B, which is known as R1, and it has a distance of suppose 2 kilometers. So something like that. This file format is important. And that for us, it would become obvious in the later parts why we are choosing this file format. So for now, just try to understand this as it is essentially an edge in our graph, but we would properly parse it and place it in our respective data structure. And also, we would need to make the nodes list from this particular data. And we can see that there are a lot of duplicate entries here. For example, if A and B are unique nodes, then A is repeating here, A is again mentioned, and then we are establishing an edge from A to C. So we would cater all these cases, we would see and we would deal with them. So let's now start. Let's get back to our coding and let's start. So first of all, we need We would just start with a basic C++ project, and let me increase the font size. Now we would use the library using namespace std. Then we would have a main function, and it would return 0. Okay, so first of all, we would need some data structures to hold different elements of graph. So as in the previous lecture, we saw that graph is composed of nodes and edges. So first class we need is node class. So let's create one. So in a node, what is required? So we would make some properties in node or data members of node, and by default they are private, so we would make them private, and then we would add some public accessor methods and a constructor here. So first of all, what do we need in a node? So in a node, we have to have distance. So what is the distance of node from particular source? Then we have to have we have to have its neighbors data. So let's include vector. Okay, so we would have its neighbors. So we would call them vector of integers called neighbor indexes. So why are we storing indexes instead of the neighbors? Because we would see that later that the graph would have a collection of nodes. So each node would be stored in an array, suppose, and that array would have an index. So we don't need to store the complete node. We have already done. We would already have that in graph. We would just need the index to actually locate that node, which is the neighbor of this node. So that's why we are using this data type. We are using a vector of integers. Then we would also need what we discussed. We would need parent index. So we would have the parent node index basically. So what is the parent node index? If it is specified, for now it won't be any meaningful value. Then we can also have node label, which we saw in the file format as well. Nodes have label A, B, C, D. And lastly, we would need to have a status is visited. Because we saw during the algorithm, the Dijkstra algorithm, it is very important that we know that if the node is visited or not. And so these are pretty much all the things that we need. So let me quickly write the constructor for this node. So let me quickly grab the constructor. So the constructor for this would be like this. So when we initialize a node, then we have to define its distance as infinity. So what is infinity? Basically, we don't have an infinity in C++. So we can define infinity as maximum possible integer which could be stored. So let me include a library called limits. So this library has the different limits for each data type. So let's define infinity as int max. So it would be a maximum integer. We would name as infinity, which is our first condition for initializing in Dijkstra, that all nodes, the distances should be marked as infinity. Then we would initialize an empty array for neighbor indexes. We would give a negative index for parent node, because -1 is basically a default index. When we are dealing with indexes in C++ or C, the array indexes start from 0, and they are all positive indexes. So if there is a negative index, it means that there is no parent assigned to this. So for now, obviously, each node will not have any sort of parent. And so we are also giving an empty label because we don't know what is the label, and we are currently marking the is visited as false. And after that, we have to basically write the setter and getter method for each property. So let me quickly go through that. We because the because these properties are private, we won't be able to directly access them. So that's why we have to write their setter and getter properties. Let me quickly show. So first of all, we have distance, set distance and get distance. So set distance would get an integer in a function, and it would set that distance of the node. And then we would need get distance to I can get the distance, what is the current distance. Set neighbors, it would set the neighbor indexes array. Get neighbors would get that array. Then set parent node index would set the parent node index. And so these are all very obvious, and it's very straightforward. Now we would write edge class. So we for edge, what do we need? So an edge has source node index. So what is the source node? Then edge would have a destination node index, and edge would also have a label, and edge would have edge cost. So I think these are the variables that we need in edge, and we would write a constructor for edge. Uh, So for edge, we have this constructor, uh, which is a parameterized constructor. We would pass in all the values at once, and we will set them. So it depends on the use case. If your data type doesn't need to specify all the values, then you can use the default constructor without any arguments. But for now, we are using this constructor. And also we would write the getter and setters for each property. So this is how we do it, similar to what we did for node. So we have source node index, getter and setter. Now we would finally write graph class. So graph class would have only two variables, two vectors, sorry, and this would be private. Then there will be some public members. So we would have two private variables called vector of node and edges. So we would have these nodes and edges because the graph has nodes and edges. And we would write its constructor. So its constructor would be very simple. It would be just initializing these arrays, these vectors as empty vectors. And then we would also write the setter and getter methods. So it's very straightforward. And we would just write getter and setter methods for this graph. So so far we have been able to write these data types, and we are done with that. Now as we have mentioned that we need to read from files, so we would include fstream library. This is used to read a file, and we would also probably need string and string to read the file line by line and pass it. So in the main method, let's think about uh, how to approach this. So first of all, we would need a file. We would need to read the file. So let's come here and let's open a stream into that file. So let me quickly write that. So we have this file info.txt. Let me show that file as well in our project. Let me quickly share my screen. So here we are, and in this folder we can see that we have this info.txt file which I showed already. So this is the file we are going to read. Make sure that this file is placed in your directory. Yeah. And after this, we need a graph. For now, this graph would be empty, but we need a graph. And we also need to read the file line by line. Let me make this declaration before this. And so for that, we need a line, which will a string called line. So this line will be a temporary variable, which will hold each line, and then we would pass that line. So let me write the code to see if to pass the file. So first of all, we would check if source city file is open. If it's open, only then we can run this code, and we would use a function called getLine, and we would pass source city file. This function reads one line from the file and sequentially, and we would put that into line. So we are saying that while we are able to get lines from the file, we should keep this file open. So now here we can define our data types. As we know that we have the syntax. Let me quickly write the syntax. So we had something like this. So the syntax of the pattern for the edge data was like this. So then it was root label, and then it was the edge cost. So we have to create the respective variables to store these. So first of all, we would say uh, source node label. So we would call it, we won't give it any value. Then we would have to have destination node label. Then we would also need to have edge label. And we also need to have an integer called edge cost. So we would need these variables, and now we have to parse these variables. So we would define an string object called ss, which would include line. So this is basically this object would be used to pass the different parts of that this line into respective variables. So uh, let's quickly grab that. So first of all, we need to make sure that we don't include this inverted comma into the name, the source label. So we have to skip that. So in order to do that, we we would use this code. Let me quickly so let me give the correct names to this, and let me explain this. So this code does what this code does is it says, okay, start reading from string stream until we find this code. So when we start it, it would finish just at this point. We would find first code, and nothing would be added in this source label. It would be empty. Then we would again tell it to read it till the next code, and put whatever is in between in this variable. So it would put this a in the source node table. Then we would repeat this process. We would say, okay, read the line up to next inverted comma, and it would read it, and it would there would be a space. So a space is not the correct destination label. So we would repeat that process. Then it would read till the next port, and in between whatever the string is, it would put into destination node. So we would have our correct source node and destination node. Then there is very simple. We don't have ports anymore, so we can easily pass the data by using this shift operator. This forward shift operator is also used in CN. So basically, it checks for the string and sees if there is a space, and if there is a space, then the whatever the thing is in between, it casts into appropriate data type. So if we place a string here, it would put it into string. If we place an integer, it would try to put it into an integer. So let's place it in edge level. So, and after that, we would put the next thing, which is an integer into edge pos. So with this, uh, we have correctly passed this edge data into different respective variables. But now we have to create nodes and edges. So first of all, we would need a helper function called insert node, and it would take graph reference and a string of node label. So let me explain what this function should do. So okay, so this function should insert a node into the graph, and as we saw that there can be many duplicates, so we have to avoid duplicates. So if there is a duplicate node, then we would need to avoid that, and we have to make sure that we get the correct node. And whenever a node is inserted into the graph, we also need its index. So because we want to store that index in our edge object as well. So this function needs to insert a node at appropriate place, and don't insert a node in case of a duplicate, and return the proper index. So for that, let me quickly write that function. So this is how this function will work. First of all, we would define an index which would contain the nodes, which would contain the current node sizes. For example, in at start, it would be 0. So our index would be 0. And then we would see if the nodes are empty, then we would simply insert it and return the index. So in that case, the first index always is 0, so it would be correct. In case the nodes have some size, then we would iterate over all the nodes, and we would see if this node label is already in the nodes. We would get each node, and then we would check its label. And if it is found, then it means that we don't need to insert it, and we would just return the index where we found it. So in that case, it would be good. And if this whole loop is executed and we didn't find any duplicate, then it means we need to insert it. So we would insert it, and we would return the index. This index would be the same, which is the size. So the previous size would be its index. So here we would just get we would insert our new nodes and get their indexes. So source node and destination node would we would get their indexes. So here we would write that. Now we also need to this is source node label, and this is destination node label. Okay, so we also need to resolve the neighbors. So if there is an edge, for example, this is an edge, then we need to insert the neighbor destination index as a neighbor to this source node. And in case also, we also need to insert the destination node's neighbor as the source node. So we have to manage the neighbors as well. So let's me write a function called insert neighbor. So insert neighbor function. Let's see how we would approach this. So here we have this insert neighbor function. So insert neighbor will take a graph, so that same graph, then it would take node index and its neighbor index. So we would give it, suppose this is our source node, we would say, okay, this we want to insert a neighbor. So let's write this also, insert neighbor, and we would give this source node index, and we would give it destination node index as the first neighbor because these are connected. So, and we would also need to give it graph. So this would make sure that this neighbor is inserted into our source nodes arrays, neighbor array. So let's go through this. We are trying to avoid duplicates here as well. First of all, we would see that if this neighbor node, this function, we would see that if the current neighbors are empty for this particular node, if doesn't have any neighbor, we'll simply just add that neighbor index. So we don't need to return an index here. So we would just add that in its array. Then if there are some already existing neighbors, then we would just iterate over them, and we would see if this index already exists. If it already exists, then we need to do nothing. And if we have traversed all this array and we found we are still here, it means that we need to insert this index into our neighbors. So it's very simple, same similar pattern, and it would make sure that there are no duplicate neighbors in this. First of all, we would use this to insert a neighbor for source node. Then we would use this neighbor here for destination node. We would give source node as its neighbor. So it would make sure that neighbors are added correctly. And there is another utility function that we would need, which is called insert edge. So let me quickly grab that function. It is a very simple function. So let's grab that function and add this here as well. So insert edge will simply take a graph and then its source node index, destination node index, and label and cost, which is basically like this file format. Same parameters would be need. So we would just call this function insert edge, and we would pass all these source node index, then source destination node index. Then we would also pass it label, edge label, and we would also pass it edge cost. And we would also need to make sure that we are passing the graph. So now when this is done, it means that our edge has also been added correctly. So with this, we can safely, when this process is done, then we can safely close our file, and our graph has been created. So let's try to visualize this graph as well, and we would just end the video there. So let me quickly see how to visualize this. So in order to visualize this, let me share my screen again. I think, okay. So if we want to visualize this properly, we have to write a small function. So let me quickly write that function. And not function, but just some information here. Let me quickly write that piece of code. So here we are just checking, okay, how many total nodes are there, and then we are just looking over all the nodes and getting the distances. Then we would see the neighbors, which node has which neighbors, and we would see some status is this node visited, and so on. And then we would also display some information about edges. So let's compile this. So let's compile this solution. So it has succeeded, and let's run this. And let me share my screen with you. So Let's see how this looks. So for now, we have 7 nodes. Yes, this is correct. Then we have first node which has node label A. Its neighbors are B and C. And then there is a second node which is called B, and its neighbors are A and D. So let me quickly show this. Let me quickly show our screen, Adobe XD screen, and just see that A has the neighbor B and C. And right now, these are node information, so there would be infinity as a their distance only. We won't see any edge cost. We would see that data in edges. So let me go back to the DOS window. Let's see what else. So this is the node data. Node and neighbors are being populated correctly. And then we would come here and see we have total 9 edges. Yes, that's correct. Then the first edge is A from A to B and its cost is 2. Then second edge is from A to C and its cost is 6. So this correctly reflects what we saw in our graph. And our data structures are working correctly. So in next part, we would explore how to write the Dijkstra algorithm on this. How would we would approach the Dijkstra algorithm, and how what other functions do we need for that? So for now, this is that's it. If you have any questions, please feel free to ask, and we will meet in the next video. Thank you for watching. Take care.